Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video, we are going to look at the implementation of the nearest neighbor methods that we have seen in past videos in Python. So we'll look at implementation of all these topics that are listed here. So let's get into Jupyter Notebook and start coding. Here I've imported a bunch of libraries. We have NumPy, Pandas, and couple of libraries from Scikit-learn, including this library for neighbors that we'll use for the K-nearest neighbor, radius classifiers, etc. So with the first, and these are the topics again that we'll cover. And in the Jupyter notebook, these are the versions that I'm currently using. Now the first topic that we'll look at is NearestCentroid classifier. So NearestCentroid classifier, and for this we will think of this as a baseline and see how what accuracy we get with this. And the data set that we'll use for this would be a toy data set. We'll use the digits data set from Scikit-learn. So data sets dot load underscore digits, and again we'll split this train x underscore test y underscore train y underscore test is equal to train underscore test underscore split, and this would be data dot target, and we can print the shape. So x underscore train x underscore test, so we check the shape, sorry, we can check the shape of each of these. So we have the shape of these, and we have around 1300 records for the train and 450 records for the test set. Now we can write the classifier. So CLF is equal to neighbors, and I'm going to copy this words because we'll be using it. Nearest centroid, and for this the metric will use the Euclidean distance, in this case Euclidean, and we'll proceed with this. And after we run this, we'll use the shrink underscore threshold to see if that has any effect. So CLF dot fit, this would be on the x train y underscore train, and then y underscore pred is equal to CLF dot predict x underscore test, and then here we can calculate the accuracy. So ACU is equal to matrix dot accuracy underscore score y underscore test y underscore pred, and then we can print this. So print accuracy ACU, and then we can also get the confusion matrix. CM is equal to matrix dot confusion underscore matrix, and this would be y underscore test y underscore pred, and we can print this as well. So print confusion matrix, and we can print this on the line below this. So we put a \n cm, and so the accuracy that we get with this is 0.89, and we can see this confusion matrix here. There are some misclassifications, but overall it's looking pretty good. Now if you remember, with the nearest centroid, there is a parameter where we can shrink the centroid. So if you look in the help section, here we see this is the shrink threshold that we can specify, and if you look in the docs, this is used for shrinking centroids to remove features. So we can specify a value there, a float value. So let's try to see if that changes the accuracy. So I'm going to use the shrink underscore threshold and set the value to 0.5, and let's see what. So it had marginal effect. If we change this to 2.5, we go up to 0.89. So that was the nearest centroid classifier. Now let's move on to KNeighborsClassifier. KNeighborsClassifier, and this will try first without any component and neighborhood component analysis, and then we'll add that in the second trial. So we still have the same data set that we are going to use. So let me print the shapes here. So that's the data set we'll use, and again this entire part of code is the same, so I'll copy paste that here. We just need to change this line. So this is K neighbors and classifier. So for this, we'll use all the default values that are in the KNeighbors classifier and run this to see what we get. So K neighbors sklearn.neighbors has no attribute K neighbors. K. Okay, so here we can see that we get around 98, 0.98 as accuracy score with KNeighbors classifier. Now, if we add component analysis to this, let's see what effect that has. So here we have KNN plus NCA, so neighborhood component analysis. So let me write that down. Neighborhood component analysis. And with this, what we are going to do is we are going to reduce the number of components similar to PCA. We haven't talked about that, but what we are going to do is right now, if we look at the shape of X-train, so X-train.shape, we have around 64 features. And with neighborhood component analysis, we are going to reduce this number of features to less than 10 and see how that works. So for this, we would need to load the data set, or maybe we don't. We can work with the X-train that we already have and see how that works. So for this, then we use NCA is equal to neighbors, sorry, neighbors dot neighborhood components. So there should be S there, components analysis. And here we'll start out with specifying n components is equal to, let's say, maybe just 3 components, and NCA dot fit. So this would fit on X train and Y train. And then we can print NCA. So with that, now what we can do is proceed with the KNN. So here we have 3 components now, and for KNN it would be the same setup that we had earlier. So you can copy and paste that here. Now one difference is going to be here, instead of using X train, we are going to use the transformed version of that. So we'll use NCA.transform X train, because we did fit the NCA up here, and so we'll use that to transform this particular data. And the same thing for X test, we can use NCA.transform X test, and with that, and with just 3 features now, let's see what accuracy we get. So here we still have pretty high accuracy. We are 0.88 and pretty close to 90% with just 3 features out of 64. Now if we change this, and let's say if we go up to 6, we should see a slight increase. So we, with 6 components, we are already at 96%. So based on the type of project you are working on, if 96% accuracy is enough, then with just 6 components, you'll be saving a lot of computational resources, to maybe, because it would expedite the training process significantly. So that's one of the use of neighborhood component analysis. Now let's look at radius neighbors classifier. So radius neighbors classifier, and for this, as we have seen in the intuition video, we can specify the radius in this case to get the nearest neighbors and then get a vote on the class to which a particular data set would belong, a test point would belong. So let me copy and we'll just run this. So we start out with that, and now we can write the classifier. So classifier code is going to be the same, so let's just copy that. And here now we have radius neighbors classifier, radius neighbors classifier, and we'll start out with specifying the radius as 1.0. That's the default. I think that's the default, so we can check if you type that with a question mark. So here the default radius is 1 and the weights are uniform, so we can change that and later on and see if that has any effect. So with this we can now run this code, and okay, so this is not going to work because we need to remove the nca underscore transform, and we'll just use the x underscore train and x underscore test. Now the reason why we are getting this error, so if you scroll down, no neighbors found for the test samples array. So possibly in the test data set, uh, with the radius of 1, it is not able to find neighbors. So what we can do is increase this value, and if we go up to 5, so we still have the error. So how about we go up to maybe 20, we still have the error, maybe 30. So all the way, even if we are at 30, we still have the error. So we can go maybe 60, and at 60 we do get result, but then the accuracy is much lower. So I'm going to try and see if reducing this down to maybe a lower number helps. So how about 35? So if we go down so to 35 as the radius, then we get an accuracy around 0.94. So if you are going to use the radius neighbors classifier, then this parameter would have to be tuned to a particular value that gives the highest accuracy. Next, let's look at the pre-computed k-nearest neighbors. So in KNN, there is a feature where we can use pre-computed graphs, pre-computed neighbors, and we can see how that can be done. So here again, we will proceed with the same data set x underscore train dot shape. So we'll have the digits data set here. Now to create the graph, we'll use the KNeighborsTransformer. So graph is equal to neighbors dot k neighbors transformer, and we can fit this. So graph dot fit x underscore train y underscore train, and we can print graph. So that's the transform, that's the fit we have for the transform. Now we can use that in the classification. So for this we can use the KNeighborsClassifier that we have used above. So let's use that there. And one difference is similar to NCA, what we need to do is transform this x train. So graph dot transform, and similarly for the x test we need to transform it. So graph dot transform, and now if we run this classifier for the k nearest neighbor, we get this output. So we have an accuracy of around 0.94 when using this one. Now here, of course, we can change this. So we can change the parameters. We can change how many values of k neighbors we have. So n underscore neighbors, and if we specify maybe 5 values, we can change the values here, and we can use the metric. So metric, so I think that's metric. Let me double check. We look at the help metric, and then we have weights. So I was looking for weights. So weights is equal to, if we use distance, then we get slightly higher accuracy. So you can try and change some of these parameter values and see if you can increase the accuracy, or you can also look at what values of parameters, if they are too high or too low, if that adversely affects the accuracy that we have. Next, let's look at KNN Regressor. And for the regressor, we'll use the diabetes dataset from Scikit-learn. So for KNN Regressor, we'll use data is equal to data sets dot load underscore diabetes, and here same as before, x train x underscore test, y underscore train, y underscore test, and this is train underscore test underscore split, and we have data dot target, and we can print the shape of x underscore train dot shape, and then we can check the shape of test as well. And we have around, it's a small data set, we have 331 for 10 train and 111 for test. Now for the classification, for the regression, we'll create this variable neigh for neighborhood. So neighbors dot k neighbors regressor, and here we can use the algorithm is equal to, we can try different. So we'll start out with the brute, then we have a KD tree and also the ball tree, and then we can fit this on neigh dot fit x underscore train, y underscore train, and then I use that to predict. So y underscore pred is equal to neighborhood predict x underscore test, and then we can get the matrix here. So the scores MAC is equal to matrix dot mean underscore underscore squared underscore error, and this would be based on the y underscore test, y underscore pred, and then we have MAE, so me matrix dot this would be absolute mean absolute error, so mean underscore absolute underscore error, so y underscore test, y underscore pred, and then we have R2 score. So R2 is equal to matrix dot R2 underscore score underscore score, and this will be y underscore test and y underscore pred, and finally we can print all these values. So print MAC, and then we have print, the next is MAE, and then finally we have print R2. So R2, and now when we run this, we get R2 squared. So we have very high MAC and very low R2 squared. So let's see if we can improve this R2 score to some extent. So if we try a different algorithm, let's say if we try the KD tree, then we get 30, 0.30. Let's add, so brute, it's about the same. what we can do here is we can try GridSearchCV and see if that helps us improve the accuracy to the R2 square value to at least some extent. So for that, we would write grid underscore search is equal to model underscore selection dot grid search with a capital S CV and neighbors dot K neighbors regressor, and within this now we can specify a dictionary of the parameters that need to be tuned. So the first one is number of neighbors, so n underscore neighbors, and then this is, let's try 3, 12, 24, 48 and 64. And next let's try the weights, and for weights we have uniform and distance. And after this we can try the algorithm, and for algorithms we have 3 options. The first one is brute, the second we can try ball tree is not um, probably shouldn't be using ball tree here because this is a low dimensional data set. We'll try it here, and KD tree is the last one, and we could try cross validation, so maybe 3. And once that is done, now we can use that to fit. So grid underscore search dot fit, and this would fit on the X train, Y underscore train, and finally we have this parameter neighborhood neigh is equal to grid underscore search dot best estimator. So we pick the best tuned parameters from there and then use that later on to fit. So we can print those values. So the best underscore estimator is going to be equal to this. And here we have the best estimator is that we use the brute algorithm, brute force, and with 24 neighbors and the weight as distance. So let's use that and see what if it changes the scores we had. So for this I'm going to copy the exact same code from above, and now because we have the best estimator already in here, we don't need this line, so we can comment that out and then run this code. So you can, as we can see, there was a significant jump. So from R2 score went from 0.30 to 0.40, and so that's a big improvement. The MSC did drop to 3000 from 3500. So but still it's much lower. Ideally, depending on the case and depending on the data, you would want the R2 score to be as high as possible. The maximum is 1, so maybe around 0.8, 0.9. So with this, before ending this video, let's check how linear regression would perform here. So linear regression, and for this we can use the same setup that we have up here and just change this particular line to linear underscore models dot linear regression, and rest will leave as is. So when we run this linear model, okay, so the linear regression does have a higher R2 value, R2 score than the K nearest neighbors that we have tried. So this is at 0.48. So that was it for this video. I hope in this video you got hands-on experience on how to use nearest neighbor methods for both classification and regression tasks. We also looked at how to create, how to use the KNeighborsTransformer to create a graph matrix that can be used as a pre-computed matrix instead of the train set. And we also looked at how we can perform a neighborhood component analysis to reduce the number of features from, I think it was 64 to just 6 features. I hope you get some practice on this. If you have any comments or suggestions, please let me know in the comment section below. I hope to see you all in the next video as well. Please like, share, and subscribe. Thank you.